Welcome to the fifth lecture of fifth module of this course called Game Theory and Economics. So, what we have done so far in this course is that we have been in this particular module we have been discussing subgame perfect equilibrium in case of extensive game. And in the last lecture we have looked at the definition of subgame perfect equilibrium and how it can be applied to games, extensive games with perfect information. While doing that, we have seen that this idea is important and in many cases we can apply it, and it has some interesting properties also. For example, if I have got a subgame perfect equilibrium, it is necessarily a Nash equilibrium also in an extensive game. So, every subgame perfect equilibrium is a Nash equilibrium because what happens in a subgame perfect equilibrium is that it induces equilibrium, that is Nash equilibrium, in every possible subgame of the game. Now, the game itself is a subgame of it, and therefore, in the game also there is equilibrium if we have a subgame perfect Nash equilibrium. So, these are important properties. However, this procedure of finding a subgame perfect equilibrium, how we did that, the idea that we invoked was the following, that suppose I have a strategy profile, then with respect to that subgame perfect equilibrium strategy profile, we shall get a corresponding terminal history, and with respect to that terminal history, the players are getting some payoffs. What we say is that there might be many subgames in that game which are inconsistent with that terminal history, which may not fall, these other subgames may not fall in the path of the terminal history. Nevertheless, in the subgame perfect equilibrium, the strategies have to be specified by the players in all those subgames which are out of the way of the terminal history also. And in the subgame perfect equilibrium, all these strategies which do not fall in the terminal history described by the strategy profile, equilibrium strategy profile, all those strategies must also be optimal. Now, just for conceptualizing this, for visualizing this, remember we do not need that the players are rational, that I know that the other players are rational, we do not need that assumption. We also do not need the assumption that the players know the structure of the game. So, these things may not be common knowledge. I may not know what is the structure of the game, I may not know that the other players are rational or irrational, does not matter. What matters is that I go to each and every subgame of the entire game and I look at the actions of the other players in those subgames. And if those actions are steady, if those actions are repeated over time, then I have got an equilibrium strategy profile, that is all. I do not need that the players, I have some behavioral assumptions about the preferences of the other player. They may not be rational, but their actions, if they are consistent, then I have a steady state. So, this is the idea of subgame perfect equilibrium. But another way to look at subgame perfect equilibrium is to rely on rationality, that the players know that they are rational. So, it is not only the fact that I know I am rational, I also know that the other players are also rational, and they know the structure of the game in the sense that what are the actions that are available to the other players when it is their turn to move. So, if the structure of the and how many stages are there, if the structure of the game is known, if rationality is a common knowledge, then we can have another interpretation of subgame perfect Nash equilibrium, in the sense that they rely on this fact that other players are rational, and therefore they can form a belief what action other players will take if they play an action. So, in this case players are not relying on experience, they are relying on the fact that the other players are rational and they also have information about the structure of the game. So, one example will be the following. Let me give you an example. And this idea that I am depending on the fact that the other players are rational and I try to find out what is the subgame perfect equilibrium, this method is called backward induction. So, let us try to apply this idea of backward induction in the familiar game, the entry game. So, this was the game, and suppose I want to invoke the idea of backward induction, then how shall I go about doing it? Now, here what I shall say is the following, that the challenger knows that the incumbent is rational. So, given that the challenger knows that the incumbent is rational, he knows, that is the challenger knows that if he takes this action in, and challenger also knows the structure of the game. So, he knows that after he has taken the action in, the incumbent will be left with two options, one is fight and the other is to accommodate. Now, since the challenger knows that the incumbent is rational, he can figure out that the incumbent will never fight. So, this is suboptimal for the incumbent because he is getting 0 here if he fights. So, therefore, the only action that is possible or that is rational for incumbent to take is to accommodate, because he is getting 1 here. So, this is what the challenger is figuring out by introspecting the game, by looking at the game and trying to figuring out what the other player will do if he takes a particular action. And therefore, the challenger will in that case what he shall do? He now knows that if he gets in, obviously the incumbent will accommodate, in which case basically the payoff can be thought of as being here. So, the challenger has to basically compare between 2 and 1. If he gets in, the incumbent will accommodate, so he will get 2. If he gets out, he is getting 1, and therefore he will always get in. So, this is the way to apply backward induction, where people are depending on each other's rationality, assumption of rationality, which is basically the old assumption that the theory of rational choice, people want to maximize their payoffs, and people know the structure of the game, and then we are trying to find out what is the subgame perfect equilibrium. And here we are seeing that in and accommodate is the, in fact there is no other subgame perfect equilibrium, this is the unique subgame perfect equilibrium in this game. So, this is the idea, and we can use this notion of subgame perfect equilibrium, this notion of backward induction to find out the subgame perfect equilibrium in other games also. But before we go into that, let me just tell you the rule of thumb, the way of doing this backward induction method, the way of applying this backward induction method. So, what we do is that we start with subgames of length 1. What is meant by length 1? Well, in any game, the length of the longest terminal history is called the length of that game. So, if I am talking about subgame of length 1, by that I mean that the longest terminal history in that subgame is 1 of length 1. So, I take each and every subgame of length 1 and I look at the player who is to move at the beginning of those subgames. So, each of these players who are going to move at the beginning of these subgames, I try to find out what is their optimal action, or in many cases it can be actions, not action. There can be more than one action which is optimal. Now, so I figure out what are the optimal actions of the players who are in the beginning of subgames of length 1. Then I go backward, and that is why it is called backward induction. I go backward and I look at the subgames of length 2. So, I take the optimal actions and then subgames of length 2. When I go to the subgames of length 2, we take these optimal actions as given and go to the subgames of length 2. And then we look at the players who are at the beginning of the subgames of length 2 and we try to figure out what are their optimal actions given these optimal actions, of subgames of length 1. And so, we again have optimal actions in this stage, and likewise we go on. So, we go on backwards from subgame of length 1 to subgame of length 2, backwards maybe 3, and till we reach the beginning of the game. And by doing that, the series of optimal actions that we trace out by this process, those series are nothing but the subgame perfect equilibria or equilibrium. So, this is basically the method. Here also that is what we have done. We started out with this subgame of length 1. We have seen that the incumbent has the optimal action of accommodate. Then taking this accommodate action as given, we went back and looked at this subgame, which is basically the entire game of length 2, and we then saw that given the optimal action accommodate, player 1 who is to move in the beginning of the subgame of length 1 of length 2 must get in. So, therefore, in accommodate is the optimal set of strategies which is known as the subgame perfect equilibrium. So, this is the idea. Now, let us step back a little bit and see how and which situations are conducive for the applications of this notion of subgame perfect equilibrium of this backward induction method. Now, obviously, if I have a game which is infinite horizon, okay, what is meant by an infinite horizon game? If the length of the longest terminal history is infinite, then we have an infinite horizon game. If the length is finite, then we have a finite horizon game. Now, this is crucial because in this case, if I have to apply the backward induction method, I have to start from somewhere of subgames of length 1. But if the game is infinitely stretched, then there is no finality, there is no end of the game, and therefore I cannot apply this method. So, this method can be applied only if the game is a finite horizon game, this method of backward induction, and that is one thing. But this method that I described here rather loosely can be tightened a little bit by stating it more formally, what is the method of backward induction. So, let us try to do that. So, this is the method formally stated. Finding subgame perfect Nash equilibrium through backward induction. There are some steps. First step, for each subgame of length 1, find the set of optimal actions of the player who moves first. So, at the beginning of the player, at the beginning of the subgame, there is a player, and we have to find out what is his optimal action or optimal actions. Index the subgame by j and denote by Sj star 1 the set of optimal actions in the subgame j. So, there might be many subgames of length 1, and they can be given index j, and by capital Sj star 1 I mean the set of optimal actions in that subgame of length 1 which is indexed by j. This is the second step. For each combination of actions consisting of 1 from each set Sj star 1, find for each subgame of length 2 the set of optimal actions of the player who moves first. So, this is just what I have said before, but more formally. From subgame of length 1, then we go back to subgame of length 2. The result is a set of strategy profiles for each subgame of length 2. Denote by SL star 2 the set of strategy profiles in subgame L. So, L is just an index. This is the third stage. Continue by examining successively longer subgames until you reach the start of the game. So, this is just induction. At each stage k, for each combination of strategy profiles consisting of 1 from each set SP star k minus 1 constructed in the previous stage, find for each subgame of length k the set of optimal actions of the player who moves first, and hence set of strategy profiles for each subgame of length k. So, just stating the induction, if you have found out what are the optimal strategy profiles of length k minus 1, then you go back to subgames of length k until you reach the start of the game. The set of strategy profiles that this procedure yields for the whole game is the set of subgame perfect equilibria of the game. So, this is the formally stated procedure of subgame perfect equilibrium. Some interesting properties of subgame perfect equilibria are the following. One is that if I have got a finite extensive game with perfect information, then there must be at least one subgame perfect equilibrium in that game. So, finite games will always have subgame perfect equilibrium. Another interesting property is that if at any stage a player has a unique optimal action, if at any subgame, if you have got a unique action for a player who is to move at that subgame, then there is a unique subgame perfect equilibrium, and this is intuitive. Okay. Now, what we propose to do now is to take another example. and let us see if we can find subgame perfect equilibrium if there is indifference, in the sense that the game that we have just seen, the entry game, was a case where a player at the beginning of any subgame is not indifferent, he has an optimal unique action. But if there is indifference, then how do we deal with that? But before talking about indifference, let us take a more difficult game where there is no indifference. So, a simpler where there is no indifference game where the actions are unique, and this is a game which you have seen before. So, this is the game, and we suppose we have to find out what are the subgame perfect equilibria, or what is the subgame perfect equilibrium in this game. Now, to do that, what we need to do is to first remember what were the subgame, not subgame perfect, but Nash equilibria of this game. The subgame perfect Nash equilibria will be a subset of this set of Nash equilibria. So, just try to remembering what are the Nash equilibria of this extensive game. There is more than one. In fact, there are three. So, C, H, F, C, H and F, this is one. D, G, E, T, G and E, and D, H, E, T, H, E. So, these are the three Nash equilibria profiles, strategy profiles. Some of them will be subgame perfect, some of them will not be. We have to find out which are subgame perfect equilibrium. Now, if I have to use the method of backward induction, then what do? I start with subgames of length 1. So, this is a subgame of length 1. In fact, this is the only subgame of length 1. And this is basically followed, this is following the history, non-terminal history CE. So, in this subgame we have to look at the optimal action of the player who is going to move in the beginning of this game. Now, this player is basically 1 because PCE is 1. Now, what is optimal for 1? Optimal for 1 is obviously G. So, G is optimal action for 1, after the history CE. So, this we are taking as given, and then we are trying to go backwards. Then basically we go to the subgame of length 2, and this is described as the following. This subgame is following the non-terminal history, C. After C, this subgame comes about. All right. Now, in this subgame where 2 is to move first, 2 basically has to compare between what and what? 2 has to compare between E and F. But given that player 1 is going to take this action G, because we know, as I just mentioned, that the players are dependent on the fact that the other players are rational. So, 2 knows that player 1 is rational. So, therefore, 2 is believing, or he is trusting the fact that 1 will take this action G. So, I can as well write this payoff here 1 2. So, the comparison is between 2 and 1, this 2 and this 1, and obviously 2 is greater than 1, and action is E, right. So, this will fall on a Nash equilibrium strategy. This will also fall on the Nash equilibrium subgame perfect Nash equilibrium strategy profile. Sorry, this E and this G. E and G, they will fall on the Nash equilibrium strategy profile. So, then we again go backward and look at the subgame of length 3. Okay. This is following the non-terminal history. Phi. And who is the player who is going to move in this subgame? It is 1, and 1 is depending on the fact that this action and this action are going to be taken by 2 and himself in the subsequent stages. So, the choice is between this and this, right, and C and D. If he plays D, he is getting 2. If he plays C, then 2 is going to play E, and in the third stage 1 is again going to play G. So, therefore, 1 will choose D. So, we have got a series of optimal actions, right. One is G, the second is E, and the first is D. Subgame perfect equilibrium profile is D, G and E. Look how I have arranged these actions. Before this comma, in this parenthesis, before this comma I have DG. DG is basically the strategy of player 1. and after the comma I have the strategy of player 2, and the interpretation is the following. Player 1 is saying that after the history phi I am going to move D, I am going to play D, and if CE is the history, then I am going to play G, right, G. And player 2 is saying the following, the player 2 is saying that if you play C, I will play E, and this is the only subgame perfect equilibrium in this game. So, this was a much easier game to solve, but it might be more complicated, as I just told, that if I have indifference between two actions for any player or more than one player, then I have to consider many optimal action profiles or many optimal strategies of a player at a particular stage, and then the task becomes more complicated. Let us take one example. So, player 1 has three actions in stage 1, that is after the history phi, C, D and E. If he chooses C, then player 2 gets to move, and he will have two options. If he chooses D, again player 2 has two options, H and I, and if he plays E, again player 2 has two options, J and K. So, there the game ends, there is no other action by any other player. And these are the payoffs. So, one needs to find out what are the subgame perfect equilibrium or equilibria through backward induction. So, we follow the rule, we start with subgames of length 1, unlike the case before, here I have three such subgames, not one. So, subgame following C, if the history is C, then I have subgame, and the player function is telling me that this is player 2 who is going to move. And what is the optimal action? This is optimal action, our actions. In this case, player 2 is indifferent. Player 2 is indifferent between F and G. So, F or G both are optimal. Then I have subgame following D, PD is equal to 2, and what are the optimal actions? Again I have two optimal actions, H or I, and lastly here however there is a unique optimal which is K. Now what is the task? I have to figure out what are the optimal strategies of player 2, right, and given that optimal strategies, I have to know what is optimal for player 1 in the beginning of the game. So, when we go back to sub games of length 1, there is just one sub game of length, sorry, when we go back to sub game of length 2, there is just one sub game of length 2. Now the point is, since there are indifference and since there is more than one action which is optimal, I have to consider all combinations of these actions. So, the strategy profiles, optimal strategy profiles, in fact there are more than one. It could be the following: F, H, K, he is saying F, H and K. So, this is optimal, but equally optimal is, for example, G, H, K, right, or for example, F, I, K or G, I, K. So, there are basically 4 optimal strategies of player 2. One is F, H, K, then I have F, I, K, G, H, K, G, I, K. So, these are the 4 optimal strategies of player 2, and with respect to each of them I have to know what is the optimal action of player 1 if I go back and look at sub game of length 2. So, here it begins after the non-terminal history phi, P phi is equal to 1, that is player 1 has to move in this sub game of length 2, and I have to know what is the optimal action or optimal actions of player 1 with respect to each of these strategies of player 2. With respect to FHK, F, H and K, the player 1 will basically compare between C, D and E. With C he is getting 3, with D he is getting 1 and with E he is getting again 1, C is best. So, C. With respect to FIK, optimal action of 1, F, I, K. Now, the choice is between 3, 2 and 1, again 3 is best. So, again I have got C. With respect to GHK, now there is a little complication, because here the choice is between 1 and 1 and 1 and all of them are equal. So, what is the optimal action for player 1 in this subgame of length 2? All of them are optimal, C and D and E, all of them are optimal. So, C, D, E. And finally, if I have got G, I, K, optimal action of 1, G, I and K, the optimal action is D, because if he plays D, player 2 will play I and he will get 2, in other cases he will get 1. Okay. And therefore, what are the subgame perfect equilibrium or equilibria in this case? C FHK C FIK then you have C GHK. Let us go to the next page. CGHK, DGHK and EGHK, and finally DGIK. So, essentially I have 6 subgame perfect equilibrium. What could be the interpretation of them? Just let me just take you through one of them, one subgame perfect equilibrium. This is CFIK. Let us look at the diagram. What this equilibrium is saying the following: CFIK. Player 1 is saying that at the beginning of the game, when the history is 5, I am going to take this action C. And player 2 is giving us the following strategy. He is saying that if the history is C, I will play F. If the history is D, I will play I. If the history is E, I will play K. And the equilibrium strategy, this equilibrium strategy profile is going to give me this terminal history, where player 1 is going to get 3 and player 2 is going to get 0. So, likewise we can interpret the other equilibrium strategy profiles. So, this is more or less it. What we have done is that we have looked at how to find the subgame perfect equilibrium through backward induction. What I propose to do now is to take another example where the action set of a player is not finite, which you have seen here. The action set of the players were finite. You could take only discrete number of actions, and it is a finite number of discrete actions. So, this is the example. Suppose this is the example. This is a case of synergic relationship, and this synergic relationship game we have seen before also in case of games where the players were taking their action simultaneously. So, those were strategic games, but they could be applied in the case of sequential game, that is extensive game also. So, this is the description of the game. Two people choose their efforts sequentially. First, individual 1 chooses her effort level A1, then individual 2 chooses her effort level A2, and effort level is a non-negative number, and individual i's preferences are represented by the payoff function ai multiplied by c plus aj minus ai, where j is the other individual and c greater than 0 is a constant. So, if this is the game, then I have to find out, for example, what is the subgame perfect equilibrium in this game. Remember, in this game player 1 is moving first. After player 1 has chosen A1 his effort level, then player 2 moves choosing A2. And let us write down the payoff functions AI multiplied by okay. C is positive, AI, AJ are also positive. Now, how to go about solving this game and finding the subgame perfect equilibrium. So, we basically follow the philosophy of backward induction. Here it is player 1 who is moving first. So, 1 is here. Now, 1's actions, it is a positive in number and it could be anything. So, suppose I take this, it stretches from 0 excluding 0 and infinity. So, A1 belongs to 0 infinity. Similarly, A2 also belongs to the same set 0 and infinity. And after A1 has been decided, A2 moves. Now, there is no particular position for this point. This point could be anywhere, it does not matter much. It is just A1. And here also A2 is decided, which is stretching all the way from 0 to infinity. And after that the game ends, the payoffs are A1, C, A1, C1, C plus A2 minus A1 and A2, C plus A1 minus A2. So, as I was telling, I have to apply this idea of backward induction. So, to do that, I have to find out in the subgame of length 1, there is just one subgame here. After history H is equal to A1, this subgame occurs, and this player function is giving me that the player 2 is moving in this subgame. Now, player 2 will choose that action which is optimal for him. So, he will try to maximize, 2 will decide A2 here by maximizing his payoff function, which is U2. This. Now, here A1 is just anything, it's a variable. So, given A1, player 2 is maximizing this function. So, how we know how to do that? It is just a quadratic function in A2. So, first order condition is that I differentiate this with respect to A2. and set this equal to 0, which gives me the following: A2 multiplied by minus 1 plus C plus A1 minus A2 is equal to 0. So, C plus A1 is equal to 2A2, which means A2 is equal to C plus A1 divided by 2. So, this is the optimal action of player 2. It is nothing but the best response function, if you remember. Player 2 is going to take this action, which is a function of A1. Whatever be the value of A1, this is going to be the value of A2. Now, what we are going to do is to now go back to subgame of length 2. So, subgame of length 2, this follows after non-terminal history phi, and first player is the player who moves here. So, one has to choose his optimal action given this. So, one maximizes U1, which is equal to A1 multiplied by C plus A2. Now, A2 is something which we know now, minus A1. And this is what? If I take half out, 2C plus C plus A1 minus 2A1, and this is A1 by 2, 3C minus A1. So, this is what player 1's optimal payoff function is, and he will like to maximize this payoff function. So, maximize with respect to A1, and now, so this has to be set, the derivative of this with respect to A1 will be set equal to 0, and that will give me the solution. Another way to look at it is this function achieves 0. So, U1 is 0 at A1 is equal to 0 and at A1 is equal to 3C, and this is a concave function. Therefore, the maximum is at A1 is equal to 3C divided by 2. So, this is the optimal action, the optimal action for player 1 in the beginning of the game, and so A2, this is A1 star, let us say, A2 star will be nothing but C plus A1 star divided by 2, and if we solve this, it turns out to be 5C divided by 4. So, this is how we can solve the games with infinite number of actions and continuous actions, and which are sequential games through application of backward induction. So, before we end this lecture, what we have done in this lecture is to look at backward induction method of solving games of perfect information, but which are sequential, which are extensive games, and this is something which we shall discuss in the next class also. Thank you. Explain how backward induction can be used to find subgame perfect equilibrium in finite horizon games. So, backward induction. So if we have a finite horizon game, then only we can use backward induction. Now in a finite horizon game, what we have is that the length of the longest terminal history is finite. So if we have that, then we can go to the last stage of the game, okay, and we can pick up sub games of length 1. What is meant by sub game of length 1? In the sub game where the longest terminal history is 1, that sub game will be called sub game of length 1. Find the optimal action, it could be actions also, of the player who has to make a move in the beginning of such sub games. Okay. So we pick up all the sub games of length 1, pick up, then find out what is the optimal action or actions of the players who are to make a move in the beginning of such sub games, then go backwards and select sub games of length 2 and find optimal actions of players who are to make a move in the beginning of such sub games. So going by this method, we reach the beginning of the game. And the resultant set of optimal actions will be the set of sub-game perfect equilibrium. So this is how we use the method of backward induction. In the extensive game depicted above, find the sub-game perfect equilibria through backward induction. So let us look at this game and find out first the sub games of length 1. There are 2 sub games of length 1 and player 2 makes a move in the beginning of both the sub games. If we look at this sub game, what is the optimal action of player 2? The optimal action, both of them are optimal actions, C and D. For sub game following A, C, D. Optimal action of player 2 for sub game following B, it's going to be F. So optimal strategies of 2, it could be C, F, D, F. All right, both are optimal. Now we go backward and find out the optimal action or actions of 1 after history 5. Okay. It depends on what player 2's optimal or player 2 strategy is. For CF, player 2's it is both A and B. So A CF, B CF are both optimal, and for DF, okay, no, for CF the optimal action is A, in fact, yes, it is A. So this is the subgame perfect equilibrium ACF, because from C player 1 is going to get 2, from F he is going to get 1, so he is going to pick this one A. And for DF it is both in both cases player 1 is getting 1, so both A and B. So subgame perfect equilibrium here is going to be A DF and B DF. So we have 3 subgame perfect equilibrium. Thank you.